as well. So again, today we're going to cover infrared spectroscopy, and then on Friday we'll take a look at mass spectrometry. And if you're in the lab right now with Dr. Lakakula or maybe with Mr. Geiger, I'm sure in those labs you're going to talk about infrared spectroscopy as well, and they'll probably even give you some practice problems to work on. But when we're talking about infrared spectroscopy, okay, which is what we're going to focus on today, the information that we're going to get from infrared spectroscopy is going to be functional groups. There we go. Oh, this is not going to be pretty. Functional groups is the information that we're going to get from infrared spectroscopy. And so that would be things like a ketone or an amine or an aldehyde or a carboxylic acid, an alcohol, that kind of thing. Whereas in mass spectrometry, there's a lot of things we can get out of mass spec, but I'd say the most important thing from mass spectrometry is going to be molecular formula. Molecular formula. And so if you've ever wondered in class, when we talk about these molecules, or you're reading the textbook and you see these beautiful molecules, they have these complicated structures. If you're wondering, how do we even know what the structures of these molecules are? Well, the way that we learn the structure or elucidate the structure of an organic molecule is by using spectroscopy and spectrometry. And so the first two forms that we look at, again, are today, infrared spectroscopy, then we look at mass spectrometry, and then later on we're going to do chapter 15 in a few weeks, where we look at nuclear magnetic resonance spectroscopy. But again, today we're going to focus on infrared spectroscopy. So, spectroscopy. What does spectroscopy mean? Well, spectroscopy is nothing more than the interaction between matter and light. Okay, so matter and light. And the matter that we are interested in this class is going to be molecules. And so we're going to be irradiating, which is essentially shining infrared light on organic molecules, and we're going to be able to get some information out of that. So light can be thought of as waves of energy or packets of energy called photons. And you would have learned this way back in your General Chemistry 1 when you started with the Bohr atom, and you learned how electrons, or Bohr postulated that electrons go in orbits around a nucleus, right? And then we said they could become excited when they absorb light, right? And when they relax, they emit light, and that's how they discovered that energy was quantized within the atom. And so we're going to talk about quantization in light today as well. So the properties of light include wavelength and frequency. And you should know what the speed of light is. Does anybody have the speed of light memorized? It's 3 times 10 to the power of 8 meters per second. So we say C is equal to 3.00 times 10 to the power of 8 meters per second. And you should also know the formula that C, the speed of light, is equal to wavelength, lambda. So wavelength is lambda, and then we're going to multiply that by frequency. Okay, so I'll highlight the frequency in green. So the Greek letter for frequency is the letter nu. Okay, so we have nu, and then we have lambda. So C is equal to wavelength times frequency. And so you would remember from your general chemistry days that the shorter the wavelength, the greater the energy of the light. And so you would have looked at these formulas here. Energy is equal to H, which is Planck's constant. So this is Planck's constant, okay, which you don't have to memorize for today, okay, 6.626 times 10 to the negative 34 and all that stuff, okay? But you can see the energy is equal to a constant times frequency. So what does that tell us? It tells us that energy is directly proportional to frequency. You can see here, frequency and energy are directly proportional, whereas if you plug in C over lambda for your frequency, right? If you solve this, okay, you'd say mu is equal to C over lambda. And so when you plug that in here, you see that energy is inversely proportional to wavelength. So what does that mean? Short wavelength, high energy, right? High frequency, high energy, right? That's the way we want to think about our about light. All right, let's move on from there. Oops, didn't mean to do that. So the electromagnetic spectrum. You, as a student who've already passed General Chemistry 1 and General Chemistry 2, should have a bit of an idea of radio waves being the longest of the wavelengths, and those are passing through us right now. I just felt one. Did you guys feel that? I'm kidding, right? But we all have cell phones, right? And we know telecommunications use radio waves, so those are going through the room right now. Then you have microwaves, which have a length of approximately 10 to the negative 2 meters. And I think I might have brought this up in class one day, but right, if you ever look at the door of a microwave, you ever notice in a microwave, they all have the same screen on them, right? And what's that screen for? It's to prevent the microwaves from coming out, right? You can look inside, but the microwaves can't escape because it can be dangerous for persons with pacemakers. And when it comes to the infrared region of the electromagnetic spectrum, which is what we're going to be discussing today, it's somewhere on the order of 10 to the negative 5 meters. Then we get up into the visible portion of the spectrum, which is between 400 and 700 nanometers. Then we go into the more dangerous, right, wavelengths, right, ultraviolet, right, harmful UV rays, right, ultraviolet, right, it's shorter wavelength, higher energy. Then we go to X-rays, right. What happens when you go to the dentist and they go to take your X-ray? What does the technician do? They run away, right? They go and hide somewhere because X-rays are dangerous, and then you get up to gamma rays, which are even more dangerous than those, right? Very short wavelengths, very high energy. So again, just to rehash, energy is inversely proportional to wavelength, but energy is directly proportional to frequency. All right, so keep that number in your brain, okay? 10 to the negative 5 meters. That's going to be the region that we're going to be probing when we irradiate our organic molecule with infrared electromagnetic radiation. All right, now, just a little bit of background about other regions of the electromagnetic spectrum and how they can be used to probe the structure of a molecule. Well, like I told you, in this chapter, chapter 14, we're going to focus on infrared spectroscopy. And what did I tell you on the very first slide? I said, what does infrared spectroscopy tell us? It tells us about functional groups. And so by looking at the infrared spectrum of an organic molecule, we can identify things like an ester or a ketone, or maybe a primary or secondary amine, etc. Later on in chapter 15, we will look at the most powerful form of spectroscopy, which is nuclear magnetic resonance spectroscopy. And the reason why it is so powerful is because it tells you the specific arrangements of the carbons and hydrogen atoms. Okay, there's some work that has to be done in order to determine what that is, but it is the most powerful form of spectroscopy. And then we have UV vis, which we don't really cover in this class, but that is related to conjugation. If you remember, conjugation is when we have double, single, double, single. That's what we look at when we look at UV vis spectroscopy. All right, so let's talk about matter. And again, the type of matter that we're going to be interested in will be molecules, okay? So matter exhibits particle-like properties, all right? So if we have a molecule, it can exhibit particle-like properties. On a macroscopic scale, matter appears to exhibit continuous behavior rather than quantum behavior. Consider the example of an engine powering the rotation of a tire. The tire should be able to rotate at nearly any rate. I don't want to spend too much time on quantum behavior, but quantum behavior is something that you've got to keep in mind when you're thinking about infrared spectroscopy. And you would have talked about quantum mechanics when you studied the atom, okay, in General Chemistry 1. Who remembers that you had a nucleus inside the atom, then the electrons are outside of the nucleus, right? 1s2, 2s2, 2p6, and all that good stuff, right? Well, do you remember that electrons could only reside in specific orbitals, right, or specific orbits outside of the nucleus? We said their energy is quantized, and they can't exist between energy levels, okay? So what we're going to be talking about in this chapter is going to be what we call vibrations, which is it's another way of describing stretching, okay? So we're stretching bonds back and forth, okay? But we call them vibrations. I know we think of in our everyday language, vibration, shouldn't that be like shaking the molecule? No, it's the bonds stretching back and forth, okay? So molecular covalent bonds are not static. They're going to stretch back and forth. And so the idea is this. So watch, I'm going to act it out, okay? A bond can stretch at a certain frequency, right? You see the bond is stretching at a certain frequency, and then it can stretch at a higher frequency. But it can never stretch at a frequency in between the two. And you're like, well, that's not true. Well, yes, it is. On the quantum, due to quantum mechanics, it can only vibrate at specific energies. Does that make some sense? Now, if you think about a tire spinning on an axis, technically you could make the tire spin at any speed, right? You could make it spin at 40 miles an hour, 40.1 miles an hour, 40.112 miles per hour, so on and so forth. But the idea is if the tire behaved on a quantum mechanical scale, it would only be able to rotate at 40 miles per hour, 41 miles per hour, right? 42. That's what quantum behavior is. And we are used to a little bit of quantum behavior in our everyday lives. One example would be, if you have a chicken or a hen and the hen lays eggs, right? You go collect the eggs, you're always going to get a quantized number of eggs. You're going to get 1, 2, 3, 4 eggs. You're never going to get, oh, today I got 4.74 eggs. No, there's no such thing, okay? It's quantized. Another example would be musical notes on a piano, right? Those are quantized as well. Anyhow, so matter exhibits wave-like properties, and on a molecular scale, matter is going to exhibit quantum behavior. And so, what I was saying is that a molecule will only rotate or vibrate at certain energies. The rotations of the molecules, we're not really interested with that in IR, but we are interested in vibrations when we're talking about infrared spectroscopy. We're going to be talking about vibrations, which again aren't like shaking back and forth, it's stretching of bonds, okay? Stretching of bonds back and forth. So for electrons and covalent bonds, like I just said, vibrational energy levels are separated by gaps. We say they're quantized, right? It's like this. The electron is at this energy level, close your eyes, open them. Now it's at a higher energy level. It was never in between the two. Now if you peeked, you'd say, I saw you move it. Well, on the quantum scale, it's never in between the two. It just goes from one to the other. So when a photon of light strikes a molecule, okay, so when a photon of infrared light strikes a molecule with the exact amount of energy needed, light is going to be absorbed and a vibrational excitation will occur. So we're going to have our bond that's going to be stretching back and forth because bonds are not static. It's some certain frequency. Then it's going to absorb just the right amount of energy and it's going to start vibrating faster. Okay, it's going to go to a higher energy level. And so infrared light generally causes molecular vibration. Different types of bonds absorb different IR energies. Ooh, that's kind of interesting. What are the different kinds of bonds that we see in this class? You're like, well, come on, Mr. Dion, there's not that many. You get the carbon-carbon bond, you get the carbon-hydrogen bond. I'm like, yeah, those are the first two. What else? Do we see carbon-oxygen bonds in this class? Sure. What about carbon-nitrogen bonds? Yes. What about double bonds? Sure. What about triple bonds, like a carbon-carbon triple bond in an alkyne? Is that possible? Yes. And so what we're getting at here is that these different types of bonds, whether it's a carbon-oxygen single bond or a double bond, they're going to absorb different amounts of energies, right, which is infrared light, okay, which, right, different frequencies of infrared light are going to have different energies, and we can plot that, okay? So eventually the absorbed energy is released from the molecule as heat. Now, when it comes to molecular bonds vibrating or stretching, okay, what we are going to concentrate on in Chemistry 3101 is going to be stretching vibrations. So you're going to see me probably write down the word stretch quite a bit in this class when I'm annotating a spectrum. But, so I just want to show you something here quickly. If we go on Wikipedia, okay, so if this link that's shown here is actually a link to Wikipedia, and if you scroll down on Wikipedia, it actually gives you very good representations of stretching, okay? Now, what we're going to be interested in this class is going to be the one on the very top where it says, you see it says symmetric stretching and asymmetric stretching. Again, we're only interested in stretching. If you take a higher level class that deals with infrared spectroscopy, you might get into the scissoring, rocking, wagging, and twisting and all that. But again, in this class, we're mostly going to be talking about stretching. So when you see me moving my hands like this, I'm talking about bond stretching. We can also have these scissoring and twisting and rocking and bending and all these different things. But again, what are we going to focus on in this class? We're going to focus on stretching frequencies, okay? And there's a reason why. It's because they're the most important frequencies in the infrared spectrum, and they're going to give us most of the information that we're going to need to know to solve any problem. Now, if you, the kind of person is like, okay, I understand this idea that different bonds are going to have different stretching frequencies, therefore it's going to cause different or require different amounts of energy to get them to stretch. Well, this is just kind of a graphical representation of that. We have the energy here on a y-axis, and you can see the energy gap between a carbon-hydrogen bond stretch, okay? You can see this energy gap is bigger than the energy gap between a carbon-oxygen bond, like that, okay? Now, a way you can think about it is imagine if I had a spring on the table, okay? Imagine I had a spring and I was trying to get the spring to stretch back and forth, okay, a little bit, right? I move it like this and I try to get it to go, right? Makes that sound, right? Now, what's going to make it stretch easier? If I have a heavy weight on the end or a light weight on the end, I'm trying to get it to stretch. Which one's going to make it stretch easier? A heavy one, right? A heavy one's going to burn, it's going to pull it, right? If I have a light one, then I'm just like trying to make it move with my hand. But if I have a big, think if you have a big bowling ball on the end and you move it, right, the bowling ball is going to pull it away. And so it actually takes less energy to get a spring to stretch when you have a heavier mass on it. And so what do these two bonds have in common? Carbon. But on this one, you have oxygen, which is heavier. And so it takes less energy to get the spring to stretch. Does that make sense? Okay. So there you go. Higher energy, higher frequency. And so again, what are we going to do in a few minutes is we're going to plot this on a graph, so to speak. So an infrared spectrometer is going to irradiate, or basically shine, is a fancy, it's just irradiate means just shine, the sample with all frequencies of infrared light. And so in the instrumentation room in our organic chemistry lab here, if you guys have taken a melting point yet, you might have noticed that there's two infrared spectrometers in there. If you don't know which ones they are, just ask your TA or your instructor, and they can show you which instrument is the infrared spectrometer. But the frequencies absorbed by the sample, what does it tell us? It tells us about the different kinds of bonds. Why? Because different bonds take different amounts of what? Energy to get them to stretch. Is light a form of energy? Yes. So we plot the amount of energy, right, the wavelength, which is required, and we see which, where the absorbances are, and that can give us information about the types of bonds that we have in our molecule. Now, I'm not going to go into some dog and pony show about how we prepare a sample for IR spectroscopy, because you're not going to be asked to do that in this class, right? This is a pencil and paper class. You don't have to go prepare samples for the IR. But in the olden days, I mean, when I was a student, we used to make them on these sodium chloride plates, and sometimes we would make these pellets. But the new spectrometers are much nicer. The ones that we have here, you literally just put the sample on the lens and it irradiates the sample. So you don't have to prepare these elaborate samples like we used to. Okay. So here is an IR absorption spectrum. So this is what an infrared spectrum looks like, and we're going to look at a lot of these today. So you can see it plots the percent transmittance, so you have from 0 to 100%. So what does that mean? It means if the line is up at the top, it means that most of the infrared light is being transmitted, right? Most of it's going through. But if you have something down here like this, what does it mean? It means the light didn't go through. Right? It means here, the light didn't go through, did it? So we say, we can call these absorbances, okay? So absorbances, or we'll just say that's an absorbance. And so you're like, oh man, this just looks like a bunch of crazy lines on a screen to me. Well, we're gonna try to make some sense out of this. And I also wanna bring up the x-axis here, which says wave number. And you're like, wave number? I thought you were talking about wavelength and frequency and all this kind of stuff. Well, wave number is what we use. It's just been accepted by the scientific community for a long time that we use wave numbers, which are reciprocal centimeters, okay? And so a wave number is nothing more than the inverse of a wavelength. And the symbol that we use for wave number, I'll write it here, it's nu, but we put a little thing on top of it like this. We put a little bar on top of it. So you don't even have to make it squiggly. You can just make a line like that. So nu with a little bar on top, that means wave number. All right. So if we move along here, and I know it's kind of hard to see what this is supposed to say, but this is just supposed to say wave number. Wave number is equal to frequency over the speed of light. Okay, that's all that says. Wave number, maybe I can get rid of that dot. Wave number is equal to frequency over the speed of light. You with me on that? Okay. Now, if you can just do a very quick bit of mathematics, or not mathematics, algebra with me. So if we say C is equal to lambda times nu, you with me on that? Yes. So then we can say wave number is equal to nu over, what's C? Wavelength times nu. Wavelength times frequency. So we can put wavelength times frequency like this. What happens? These cancel out. And so as I was saying, wave number is nothing more than the inverse of the wavelength. So if you take the inverse of the infrared wavelengths, which are times 10 to the negative 5 meters, as we saw when we looked at that electromagnetic spectrum, you're going to get wave numbers from 4,000 to 400 reciprocal centimeters, okay? And so the shorter the wavelength, right, it's going to give us the higher the wave number. Does that make sense? Okay. So here we're going to have high energy high energy, and here we're going to have low energy. All right, there's enough of that. Let's move on from there. Now, a signal, or an absorbance, as I called it on the previous slide. So you can put here absorbance on the IR spectrum, or a signal or a peak, okay, has three important characteristics. So one is going to be the wave number, and the wave number is just where it comes out on the x-axis. So for this one here, you might say, if you draw a line here, you see this is 3,000, 3,100, 3,200, 3,300, 3,400. So you say this is at about 3,400 reciprocal centimeters. Okay, so that's a wave number. Then we have the intensity. That's how much of it is absorbed. Okay, so we would say here that this, has a very low transmittance, this peak here. And so we would say that has a high intensity, whereas you would say something like this has a very low intensity, right? Very little there. And then we have the shape. You notice that some of these peaks, some of them are broad, okay, like this one, and then some of them are sharp, right? You look for one that's sharp, I don't know, something like this, right? So what we're going to do now is we're going to discuss the wave number. Then we're going to discuss when is a signal going to be intense, when is it going to have, a high absorbance or a low absorbance, and then we'll talk about whether it's going to be sharp or broad, okay? The most important of these is the wave number. And so I have a handout for you. If you didn't get it, don't worry about it. You're like, oh, I need this handout. It's just 2 pages that are from the slides that are in the slide deck is all it is. I'm going to put them on the screen, but if you want to grab one when you leave, okay, just take it with you. You can use it when you're studying. Again, I will put them on the screen. There's no secrets in my class. So, signal characteristics. So now we're going to discuss this whole wave number, right? And remember, the wave number was on the x-axis, so to speak, of our infrared spectrum, right? It went from 4,000 to 400 reciprocal centimeters, and we said that wave number is equal to 1 over our wavelength of our infrared light. All right, so the frequency or wave number for a stretching vibration depends on 2 things. 2 things that you guys know pretty well. One would be the bond strength. Now let me ask you guys a question. What is stronger, a single bond or a double bond in chemistry? A double bond, right? And they get stronger as you go from single to double to triple. So if we see a triple bond, it should have a higher stretching frequency than a single bond, right? So it says it depends on bond strength. So we're going to see that in a second. And it also depends on the mass difference of the atoms bonded together. Now, if you take a look at the formula here for wave number, you're like, holy heck, what am I going to do with all that? Wave number is equal to 1 over 2 pi times the speed of light. No calculators in this class, keep in mind. Okay, multiplied by the square root of F, which is the force constant, which is nothing more than bond strength. Who here remembers studying F is equal to Kx, right? And studying springs in physics class. Did anybody else do this in junior high school or high school? Yeah, so force constant of a spring. So the stronger the bond, the higher the wave number. You see that they're directly proportional. So you can say here, wave number is proportional to F, which is bond strength. So the stronger the bond, the higher the number. And then we have reduced mass. If you're like, what's a reduced mass? Well, maybe if you've taken a math class or an advanced physics class, you might have seen this before. But reduced mass is nothing more than the product of the masses of the 2 atoms in the bond divided by the sum of the 2 masses of the atoms that are in the bond. And so what's our conclusion? Well, I already drew one of them up here, which is frequency is going to give you a stronger bond is going to give you a higher stretching frequency. And then the second conclusion is going to be a larger mass difference is going to give you a higher stretching frequency. All right, so let's take a look at these 2 here. All right, let's take a look at these trends. If you're like, I'm not sure about these trends, let's start with the one on top first. I'm going to do it a little bit backwards from what's shown here. So what did I tell you first? I said that wave number was proportional to F, which is just the bond strength. So our conclusion is the stronger the bond, the higher the wave number. Remember, our wave numbers range from what? 4,000, that would be the highest, to 400, that would be the lowest. Well, look at this trend down here. Which one of these bonds is the strongest? The CN triple bond or the CN single bond? It is the triple bond, exactly. And what does it have? The highest wave number, right? Highest energy. So strongest bond. Strongest bond. And you could put their highest wave number if you want to. I'm not going to put it in there. We'll put here weakest bond. Here. All right. Nothing major there. Now, if we think about the reduced mass, which is the product of the masses of the two atoms in the bond divided by the sums, well, what does that mean? The reduced mass is going to get bigger as we have larger atoms, okay, heavier atoms, and it's in the denominator, right? And so what does that mean? It means the heavier mass we have, the lower the wave number is going to be, right? The less energy, the less that it takes to get that spring to vibrate, okay? And so we have carbon-hydrogen, which is way up at the top, right? It takes a lot of energy to get that thing to move, right? Because hydrogen is the lightest atom in the whole periodic table. The reduced mass, what's 1 times 1? Or sorry, what's, 12 times 1 is 12. Then divided by 13, right, is what you would do compared to, 12 by 35, divided by the sum of 12 and 35, right? Does that make sense to everybody? And so you can see here the carbon-hydrogen bond. If we compare it to a carbon-deuterium bond, they're both single bonds, but you see the heavier the atom, the lower the wave number. Does that make sense to everybody? Okay, the less energy it takes to get that thing to vibrate. All right, so now, and you might want to use the handout, but I don't think you really need it to solve this problem. So if you don't have it, you don't need to panic and get up and run to the front of the class or anything. It's not going to be a big deal. It says, for each of the following compounds, rank the highlighted bonds in terms of wave number. Now, if we want to rank these in terms of wave number, okay, we have a carbon-carbon triple bond, we have a carbon-carbon double bond, and then we have a carbon-hydrogen bond. So if we look at all of these, right, a carbon-hydrogen bond is pretty high. It's around 3,000, right? It's around 3,000. And if you look at the handout that I gave you, I don't even have one, okay? But if you look at the handout, if anybody wants to come grab one, I'll put them here if you're like, I need to have one, okay? If you look at the handout that I brought this morning, you'll see a carbon-carbon double bond is between 1,600 and 1,700, and a carbon-carbon triple bond is between 2,100 and 2,200. So I'll write down the stretching frequencies here. So the triple bond is going to be between 21 and 2,200 reciprocal centimeters. A double bond is going to be somewhere between 1,600 and 1,700 reciprocal centimeters. And as you saw from the previous slide, if we have a carbon-hydrogen stretch, that's way higher than any of those, right? It's around, what does it say? I'll put here greater than 3,000. We'll just put around 3,000 reciprocal centimeters. And so the answer is going to be this bond here. Okay, that one's going to have the highest wave number. Does that make sense? Okay, so this one would be highest. So we'll put here highest. And then the double bond is going to be the lowest. So we'll put it down here, lowest. All right. So now, when we go to the next one, all right, we have the carbon-hydrogen bond, which we saw before, has a wave number of about 3,000 centimeters to the -1. But here, we have a carbon-carbon single bond. Does anybody see a carbon-carbon single bond in there anywhere? Is there a carbon-carbon single bond in the table that I gave you? I don't know if there is a carbon-carbon single bond in there. Anyhow. But even if we don't have a carbon-carbon single bond in there, well, which one's going to take more energy to get to stretch? A carbon with a little old hydrogen on it, or a carbon with a big old carbon attached to the end? Right? The one with the hydrogen should have a higher wave number, right? So there we go. So we're going to put here highest, and here we'll put lowest, okay? There's always a rationale for everything. If you're wondering why isn't the carbon-carbon single bond on there, I'd say borderline too ubiquitous, right? There's too many carbon-carbon single bonds. It's just going to be noise in the spectrum. All right. Now, a little bit more about this handout, okay? And if you're wondering what's the handout, all it is, I'll just skip down to it, so just give me a second. We haven't even gotten there yet, but I'm going to keep going. Come on. Jeepers. Here it is. This is the handout, okay? So this is table 14.2. I highly suggest you try to memorize as many of these absorbances as you can, okay? Table 14.2, there's all these ones here and all these ones here, and we're going to go over them in a little bit, so don't stress about it too much yet. Let me go back here. come on. There we go. All right, so what's the conclusion we can draw? Like I said, triple bond is stronger than a double bond, which is stronger than a single bond, and that's what we see here, right? Wave number is directly proportional to bond strength, right? Higher wave number for a stronger bond. And if you're like, yeah, but come on, bonds to hydrogen, that's not a strong bond, that's a single bond. That's true, they're not as strong, but what's the deciding factor here? It's not the bond strength, it's the mass of the atoms in the bond, right? Because hydrogen only has a mass of 1. And so here the trend we're going to use is going to be mass. Okay, so we'll put here wave number is inversely proportional, okay, to reduced mass, but hydrogen is equal to 1. Okay, it's the lightest atom in the whole periodic table. Therefore, right, it's so light it takes a lot of energy to get that bond to vibrate. There we go. So we're going to use carbon-carbon double bonds, triple bonds, and bonds to hydrogen most of the time. This region of the infrared spectrum, we call this the diagnostic region. Diagnostic region. And then this region here from like 1500 below, we call this the fingerprint region. Okay? Fingerprint region. It's like this. Can you tell two people apart by their fingerprints? Sure. But if I just look at two people, right, I'm not going to tell them apart by their fingerprints, right? I'm going to tell them apart by something that's a lot more abundantly clear, like maybe their faces, right, which are going to be a lot easier to recognize than their fingerprints. And so the diagnostic region would be like the face, right, and the fingerprint is like a fingerprint, right? It's tougher to decipher a fingerprint. So again, above 1500, that's where we, in this class, and if you're in Dr. Lakakula's class or Mr. Geiger's class, it's going to be the same thing. You're going to spend 99% of your time in the diagnostic region. Why? Because it provides clear information, okay, very clear information. Whereas in the fingerprint region, it can be tougher. I will refer to the fingerprint region a few times with you guys, though, today. So let me give you an example. Check out the infrared spectra of these two compounds. Now, this compound here, this is called 2-butanol. And this compound here is called 2-propanol. And you might know 2-propanol is just rubbing alcohol that you could buy at the drugstore or something like that. Now, if I take my ruler and if I draw a line on these at 1500, okay, so if I draw a line here, oops, come on, ruler, there we go. And if I draw a line here, you'll notice that to the left of that ruler, you notice that they're pretty similar, don't you? Right? They both have this big, broad absorbance here, right? They both have some kind of spinach around here. They both have this little kind of, something up there, okay? They both look pretty similar, right? If you looked at them quickly, it's tough to distinguish them, right? Because they're very similar in the diagnostic region. But if you did want to tell the difference between these two molecules, which are very similar molecules, are the fingerprint regions the same in these two guys? No, they're very different, aren't they? Okay? Now, again, we're not going to worry about the fingerprint region a whole lot, but I'll just tell you, if you have two molecules that are very similar and you can't use the diagnostic region, then you might have to get into the fingerprint region, but we won't stress about that a whole lot today, right? We're just learning the subject. Now, when it comes to carbon-hydrogen bonds, right, the only kind of bond you can have between a carbon and a hydrogen atom is a single bond, right? Because hydrogen only has one valence electron. Well, if you haven't heard this before, you're going to hear it from me today, that it turns out that the carbon-hydrogen bond is actually affected, the strength of the bond, I should say, is affected by the hybridization of the carbon it's attached to, okay? So it turns out that as you go from sp3 to sp2 to sp, they increase in strength. And so this carbon-hydrogen bond is going to be the strongest one, whereas this one is going to be the weakest. And it has to do with the size of the hybrid orbital, right? When you have a triple bond on the carbon is sp hybridized. It's a smaller hybrid orbital than an sp3. So I'm not going to go into that whole thing. However, you see what's manifest here. How many times have I said this already today? Wave number is proportional to what? Bond strength? Yes? Did I say? I said that many times, right? So look at this. Strongest bond, highest wave number. And so you're looking at it and saying, hey, Now, I would be able to distinguish between an sp2 hybridized carbon-hydrogen stretch versus sp hybridized carbon-hydrogen stretch and sp3 hybridized carbon-hydrogen stretch, right? You can tell the difference between them. And so if you have something around 3100, that's going to be an sp2 hybridized carbon, so maybe on an aromatic ring or an alkene. Whereas if you have a terminal alkyne, you're going to see a stretch at 3300. And you see this is actually, outside of a carbon-carbon bond, this is the most ubiquitous bond in all of organic chemistry, right? How many, if you guys practice drawing your Lewis structures at the beginning of the semester, how many carbon hydrogens, single sp3 hybridized carbon-hydrogen bonds did you draw? Lots, right? You get lots of them. So look at this. It says around 2900. Now you guys are all very astute. I know that. What do you notice about these two spectra? You see where you see the number 3000 there? You see the number 3000? It's right here. Okay, I'll circle it in green. 3000. Well, 2900 is just below 3000. Look at this. There's a huge bunch of signals there. There's a bunch of absorbances here. Look at this molecule. Same thing. You see a bunch of them here just below 3000. And so most, not all, but most of the spectra that we look at are actually going to have a stretch or multiple stretches right below 3000, around 2900. Why? Because sp3 hybridized carbon-hydrogen bonds are one of the most ubiquitous bonds that we see in this class, right? It's like never ending, right? So a lot of, I'd say most of the time we don't even annotate those. We don't even bring them up because they're just so common, unless we have to for some kind of reason. All right, so here's an example. You see a line drawn here at 3000 on each of these spectra. What did we say? We said an sp hybridized carbon-hydrogen stretch was at around 3300. Well, look, there's 3000, there's 3200. That would mean 3300 would be right around here. Well, lo and behold, you have a stretch here. That tells you you have an sp hybridized carbon-hydrogen stretch. Here you have one at 3100, which you see for an alkene, right? Why? Because an alkene has sp2 hybridized carbons. If they're bound to a hydrogen, you're going to see that. And then the alkane, what do you see? Just a big old lump. A whole pile of stretches below 3000. Why? Because there's so many of those different carbon-hydrogen bonds in a molecule. All right. Now, just because you don't see a certain signal that you might hope to see doesn't mean that the functional group isn't there. So let's say you think, okay, every time I have an alkene, right, there's an alkene, a carbon-carbon double bond, I should see some kind of stretching at around 3100 reciprocal centimeters. Well, if you have a tetra-substituted alkene like this one here, right, 4 carbons attached to the 2 carbons in the double bond, you're not going to see any signal at 3100, would you? There's no carbon-hydrogen bond there, right? Right? Same thing with an alkyne. You might think, okay, every time I have an alkyne, I'm going to see that stretch at what? It's going to be at around 3300 reciprocal centimeters. Well, that's not necessarily true. What if you have an internal alkyne? So an alkyne that has carbons on both sides. It's still an alkyne, but you don't see any stretching, okay? So remember, in science, you can't prove something by a negative proof, right? I don't see it, so it's not there, right? That's not being scientific, right? You have to prove it unequivocally that it's there or not there. All right, now, let's take a look at question 14.2. For each of the following compounds, determine whether you would see a signal in the IR spectrum to the left of 3300. So we'll take a look at these. So if we take a look, you know what I'll do? I'll draw a line like this, okay? What do we see to the left of 3000, excuse me? We would either see a bond, right? A carbon-hydrogen bond from an sp2 hybridized carbon. That would be at around, what, 3100, right? Or we would see a bond from an sp hybridized carbon, and that would be at about what? 3300, right? At about 3300 reciprocal centimeters. So in the compound in the top left, excuse me, would you see any single signals above 3000 for this one? Yeah, sure, right? I see everybody nodding, right? Everybody says, yes, there's an this carbon is sp2 hybridized, and therefore this stretch is going to be at about 3100. So this will be at about 3100 reciprocal centimeters. Now what about the compound just to the right of it? Will I see any stretches above 3,000 for this guy? No, right? Because look at the two carbons in the double bond. Do either of those carbons have a hydrogen attached to them? Nope, they're attached to 1, 2, 3, 4 carbons, right? So if you looked at the spectrum, you won't see that signal at 3100, but does it mean there's no alkene in there? No, not necessarily. There is an alkene in here, all right? And don't worry, we're going to figure out how to determine that sooner or later, all right? What if we look at this guy here? Would I see a stretch above 3,000 reciprocal centimeters? Anybody? Right, I see a bunch of people saying no, right? There's nothing there. So we'll put here next to this guy, we'll say no. And here we'll say no. Why? Because these two carbons are attached to nothing but carbons. But what about this guy in the bottom right? Are you going to see something there? Yes, you have an sp hybridized carbon hydrogen stretch. And so this is going to come out at what? What's the number for it? 3,300. That's right. Don't be afraid to just yell it out in my class. There you go. Cool. So we're starting to piece things together, what we might see in our infrared spectrum. Now, in terms of the wave number, we said that wave number is affected by bond strength, right, and the mass of the atoms in the bond. So we're going to talk about bond strength for a couple more seconds here, and we're going to bring up the concept of resonance. You're like, oh boy, chapter 2, right? Chapter 2, it's back, right? Talking about resonance again. So it turns out that resonance affects the strength of a bond, right? If we have a double bond that has a resonance structure where it's a single bond, we know it has some double bond character and some single bond character. And so if I look at these two ketones that are shown here, I'll draw a line down like this, okay? Can I draw a resonance form for this guy? Yes or no? Absolutely I can, right? We know that. We studied this in detail. We have a double bond between atoms of differing electronegativity. I could draw a resonance form that looks like this, right? Only one resonance form. Could you guys tell me, for this guy here, how many different resonance forms you could draw, including this one? Does anybody know? There's two more, okay? There's two. There's going to be one that has the positive charge on this carbon, and then there's going to be one that has the positive charge over here. Check it out, okay? Here are the resonance forms, okay? This is the one that I drew on the previous slide, and this is the one I asked you about. I said there's a positive charge on this carbon, and there's a positive charge on this carbon. So now, if I highlight this carbonyl in yellow, and I highlight this carbonyl in green, if we look at the resonance forms, which one of those carbonyls has more single bond character? The one highlighted in yellow or the one highlighted in green? The one in green, right? There's two resonance forms that have single bonds, right? Whereas the one in yellow only has one resonance form where it has a single bond. So therefore, it would mean the carbonyl with more resonance forms is weaker. It's a weaker bond. And so what's the conclusion that we can draw? Is that this is a weaker CO bond, right? And we know that wave number is proportional to bond strength. On strength. Again, I'm writing this down for like the 10th time. What do you notice? It absorbs at a lower wave number, 1680 reciprocal centimeters, as opposed to 1720. So what's the effect of conjugation? What does it do to our wave number? Does it bring it up or down? If we have more resonance forms, is it going to make it stronger or weaker? Weaker. The more resonance forms we have, the weaker it's going to be. All right, there we go. So you can see here for an ester, and then we have an unsaturated ester. And so we have a ketone, which is at 1720. Then we have a conjugated ketone, which is weaker, right? The carbonyl is weaker, so that's going to absorb at a lower wave number of 1680. Then we have, a conjugated ester, like this one here, right? You could draw resonance forms for it, so it's going to be below 1720 as well. All right, let's keep going. So let's try a practice problem here. It says, each of the following compounds contains two carbonyl groups. Identify which of the carbonyl groups exhibits a lower wave number. So I'm going to highlight this one in green, and I'll highlight two carbonyl groups. Yeah, so we'll do, we'll do it like this. I'll draw a line down the middle. So we're just going to concentrate on the one on the left to start with. So we have this carbonyl in green, and then if I highlight this carbonyl in yellow, which one of these is going to have a lower wave number for the carbon-oxygen double bond for its stretch? The one in green or the one in yellow? Which one of those bonds is weaker? The one in yellow, right? Because I can draw resonance forms for it, okay, like this. And so this one will be lower wave number, right? Because it's weaker. I'm not going to write down wave number is proportional to bond strength anymore, okay? Now, if we look at the one to the right of it, I'll highlight this one in blue, and then I'll highlight this one in red. Which one of those is going to absorb at a lower wave number? The one in blue or the one in red? The one in blue, right? Because I can draw a resonance form. I can draw two resonance forms, okay? And so this one is going to absorb at a lower wave number. Cool beans? Does that make sense to everybody? All right, so if we look at use resonance structures to explain why the carbon-carbon double bond in the conjugated compound produces a lower wave number. Well, if we draw a line down here, okay, this one, there's only one resonance contributor, okay, only one resonance form, okay, outside of this one, and that would be delocalizing these electrons up here, right? But how many resonance structures can we draw besides this one here? How many more resonance forms can we draw? There's two more, right? We can draw one where we delocalize the electrons up here, and then we can draw one where we delocalize these electrons over here. In the interest of time, I'm not going to do it. So this is why, so we'll say here, more resonance forms. Resonance forms, therefore, lower wave number. All right. Everybody read the textbook before coming here this morning? Good. All right. So you're going to, if you're like, oh, crap, now you're bringing up resonance, oh, jeepers, right? Just remember, organic chemistry comes at you fast, okay? And I don't mean that in an intimidating way. Just remember, all those things that we learned, resonance, nomenclature, it's going to come up over and over in every class, right? IR, once we learn today, it's going to be important for the next class and the next class and the next class, okay? It's very cumulative, the subject, all right? Now, when it comes to the intensity of the infrared signal, I'm going to spend about 60 seconds on this because there's no point in spending any more time. But the way that you can think about it, the absorbance intensity is just related to the polarity of a bond. That's all it is, okay? So the more polar a bond is, the stronger the signal. So we'd put here more polar bond, and here if it's weak, we'd put less polar bond. That's it. Now, if you're the kind of person that's like, well, give me an explanation. The way that it works is like this, okay? When a bond starts stretching back and forth like this, its dipole moment is going to oscillate back and forth as well. And so if you remember the formula for dipole moment, and even if you don't, it doesn't matter, okay? But it creates an electric field. And so what that does is it kind of acts like an antenna. That's why I put this picture of an antenna on here, because the more polar the bond, it's like a stronger antenna, and it picks up more of the infrared signal, and you get a stronger stretch. All you need to know for this class is greater bond polarity, stronger infrared signal. That's it. So when you see something that's a very strong absorbance, a really big stretch, you're going to say that's a very polar bond. If it's just something tiny, you'll say, that's non-polar, right? So that's the only conclusion you need to draw from that. Here's a picture of it. Here we have a carbon-carbon double bond stretch. Is a carbon-carbon double bond, is that as polar as a carbon-oxygen double bond, right, Heidi? Not even close, okay? So we'll just right here, we'll put more polar, right? More polar, and so it picks up more of that infrared electromagnetic radiation, and it gives you a stronger signal. Cool? That's all you need to know. More polar, stronger stretch. Nothing more than that. Okay, let's move on from there. Now, if a bond is completely symmetrical, then you're not going to see any stretching in the infrared spectrum. And like I told you, you can't prove something by a negative in chemistry class, right? You're not allowed to do that. And so if we look at this compound here, is there any dipole between these two carbons that are highlighted? No, it's completely symmetrical, so it's completely nonpolar. So we don't see the signal for a carbon-carbon double bond, which should be somewhere in the range of 1600 to 1700, but does it mean there's no double bond? No, it doesn't necessarily mean that. You'd have to, and if you're like, well, how would you know? You'd have to use another form of spectroscopy to determine that. All right, so stronger signals are also observed when there's multiple bonds of the same type of vibrating. And so even though sp3 hybridized carbon-hydrogen bonds are not very polar, why do they give such strong signals below 2900? It's because there's so many of them, right? There's so many carbon-hydrogen single bonds in a molecule. And so you can read this part about the breathalyzer. I'll skip that for now. But anyhow, let's see if we can tackle these ones here. It says, for each pair of compounds, determine which carbon-carbon double bond will produce a stronger signal. Now remember, what our conclusion was, we said stronger signal is going to come from the more polar bond. Okay, so there's two examples here. Let's just do this one. If I highlight this double bond in yellow and this double bond in green, which one of those do you think has a stronger dipole? The one with the chlorine on it, right? Absolutely. So we'll put here stronger signal, right? The next one's a little bit tricky, right? Because you're like, well, I've got a dipole going this way and I got one going this way, and overall the net dipole is going to be going in that direction, right? But on this one, they're both pulling like this in this direction, which is actually going to be stronger net effect because they're on the same carbon instead of on two different carbons. So we'll just put here stronger signal for this guy, stronger signal, all right? And what about this one here? It says this carbon-carbon double bond produces an unusually strong signal, explaining using resonance structures. Well, even though it's just a regular old everyday carbon-carbon double bond, does it have some single bond character in there? Is there some delocalized charge in there? Absolutely, right? We could draw both of the resonance forms like this. Okay, so let me get my pen out here. We could draw this resonance form where our double bond in the ring is still intact. We have our negative charge here, a positive charge here. And then we can draw another form where we're going to show a positive charge on one of those carbons of that double bond. So is there a dipole in there? You bet your bobby socks there is. Oh yeah, big time. Right, there's a beautiful dipole in there. All right, there we go. And so we have a delta plus. Look, we have a delta plus. Delta plus right in there, right? And so we know there's a dipole in there, right? That bond is polar, right? The only way you'd know that is by understanding resonance. Does that make sense to everybody? You'd have to know that. Good. Let's move on from there. So it says trans-2-butene does not exhibit a signal in the double bond region of 1600 to 1850 reciprocal centimeters. However, infrared spectroscopy is still helpful in identifying the presence of a double bond. Identify the other signal that would indicate the presence of a carbon-carbon double bond. So I'll draw the structure of trans-2-butene, which is this, okay? Now that molecule, there's symmetry in that molecule, isn't there? And so our carbon-carbon double bond is going to be completely nonpolar. All the whatever little bit of dipoles there are in there, they cancel, right? So this bond is non-polar, and so it's not going to give you any signal in the region of 1600 to 1700 reciprocal centimeters. So how would you know there's an alkene in there? What other little piece of evidence could you get out of this that we've talked about earlier today? How would you know that there's an sp2 hybridized carbon in there? The carbon what bond? Carbon-hydrogen bond, exactly, right? It's because of this bond here, right? And we know that this stretch is going to come out where? What did we say? We have an sp2 hybridized carbon-hydrogen stretch. It's going to be at about 3,100 reciprocal centimeters. So that's going to be proof that we have our carbon-carbon double bond in there. Even though we don't see the carbon-carbon double bond in the infrared spectrum, we see the sp2 hybridized carbon-hydrogen stretch in the infrared spectrum, right? It's like putting a puzzle together, a lot of this stuff. All right, now, whether a signal is broad or sharp has to do largely with hydrogen bonding. You guys remember the topic of hydrogen bonding from General Chemistry 1? You learned London forces, dipole-dipole forces, and then hydrogen bonding. Well, whenever you see something broad like this, it usually means you have some kind of hydrogen bonding, okay? And the reason why is when you have a hydrogen bond, so here we have a bond between an oxygen and a hydrogen, And if you look at the handout that I gave you, it says that the stretch between an oxygen and a hydrogen of an alcohol is between 3,200 to 3,600 reciprocal centimeters, right? That's like from here to here, right? It's this whole big thing here, which is the OH stretch. Now, why is it so broad? Well, we said that wave number was directly proportional to bond strength divided by the reduced mass. Well, the mass of the atoms isn't changing, but is the bond strength changing during hydrogen bonding? The answer is yes. When it makes the hydrogen bond, and that's what this is right here, this is our hydrogen bond. When you make the hydrogen bond, it starts to stretch that oxygen-hydrogen bond, right? And then it flexes it back, and then it stretches it back and forth. So if the bond is getting weaker and then stronger as it's being pushed and pulled and pushed and pulled when it's hydrogen bonding, what's that going to do? It's going to change the strength of the bond. It's going to make it weak and then strong and then weak and then strong. And so what do you end up with? You end up with a big old broad signal like that because there's a range of stretching frequencies. Why? Because there's a range of strengths as it gets pushed and pulled back and forth. Does that make sense to everybody? Now, there are some times when you have an alcohol and you won't see broad stretching, but the only time that would happen is if your sample is so dilute that there's no hydrogen bonding, taking place. And I'm not going to ask you about that on your quiz. Okay, so I'm not going to ask you about free hydroxyl. I'm not going to put that on there. So if you see a broad stretch between 3,200 and 3,600, that's going to be an alcohol. There you go. So an alcohol is, I won't say it's the easiest, but it's one of the easiest stretches to recognize because it's so big that it's abundantly clear that we have that. Now, if you're like, okay, what other functional groups can participate in hydrogen bonding? What about a carboxylic acid? Can that participate in hydrogen bonding? If you don't believe me, which I know you all do, okay, but let's just zoom in. See, this is one carboxylic acid here, and this is another carboxylic acid here. Is there some hydrogen bonding taking place between these two? Yeah, we call this a dimer sometimes. We refer to this as a dimer, okay? And you can see there's intense hydrogen bonding here and intense hydrogen bonding here. So what's the net effect on the oxygen-hydrogen bond? Well, it turns out, and I can say this, like I can make this bold statement, that a carboxylic acid is the easiest functional group to recognize in the infrared spectrum. It's because the oxygen-hydrogen stretching is so broadened by that push and pull, that stretching and pushing due to the hydrogen bonding, that the stretch is really broad. Now, if you look at the handout, you'll see that the OH stretch for a carboxylic acid, you'll see it has a range of 2,200 to 3,600 reciprocal centimeters. It's massive. I mean, look at the size of that thing. Is that big enough for you? Okay, that's a huge stretch that's in there. And so you can look at that immediately and say, there must be a carboxylic acid in there. Furthermore, a carboxylic acid has a carbonyl group in it, right? And a carbonyl is going to have an absorbance around 1,700, and so this is the absorbance of the carbonyl. I guess it was already labeled on there. I just decided to give it a belt and suspenders, right? 2 labels. There you go. Anyhow, so again, I went over the concept of a dimer and hydrogen bonding. Now, if you're like, what other kind of functional groups do we cover that can hydrogen bond? I've got an alcohol. I've got a carboxylic acid. Do you guys remember amines? Yeah? Well, it turns out there's 2 types of amines. There's an amine where you have a nitrogen with 2 hydrogens on it. This is what we call a primary amine. Where's my highlighter? I'll call this primary amine, okay? So this would be a primary amine. And a secondary amine is when you have, 2 R groups and only 1 hydrogen. So we would call this a secondary amine, is this guy here. Now, it says here, secondary amines exhibit only 1 signal for the nitrogen-hydrogen bonds, whereas primary amines give you 2 signals. Now, students will oftentimes think, well, it's because if you've got 2 hydrogens, 2 signals, right? If you've got 1 hydrogen, 1 signal. It's actually... I'm not leaving. All right, anyhow. I'll go down with the ship, okay? Well, the reason why I put this picture on here, it's because when you have a primary amine, so 2 hydrogens, there's 2 ways it can stretch. I'm only going to do this once, okay? It can stretch symmetrical or asymmetrical. Okay, those are the two types of stretching. That's why you see two signals. Whereas if you have a secondary amine, it's only got one hydrogen, so there's just one signal. That's all you get, okay? So I'm done, all right? So you can see here for this would be a primary amine, so it has two signals. Now if you're like, those are so minuscule. Those are baby signals, Mr. Dion. Why are they so tiny? What's more polar, an oxygen-hydrogen bond or a nitrogen-hydrogen bond? Who's more electronegative, oxygen or hydrogen? Oxygen, right? So it's because the nitrogen-hydrogen bond, it's polar, yeah, but it's not as polar. And so are they broad? A little bit. But are they as intense? Not nearly as intense. Okay, so these are the, right? You see, these are the kind of things we look for. Anyhow, so I'm done acting that out. So let's just see here. In these spectra, if I call this, I'll call this A, B, C, and D. Based on what you've seen this morning with me, do you guys see an alcohol on here anywhere? And remember, there's no trick questions in my class. Which one is it, Kai? A. It's A, right? If you have the handout, even if you don't, right? If you have an oxygen-hydrogen stretch in an alcohol, it stretches from 3,200 to about 3,600 reciprocal centimeters. It's broad, right? It's got a pretty decent intensity because an oxygen-hydrogen bond is quite polar. So we've identified an alcohol. Do you guys see a carboxylic acid in here? I see everybody smiling. Which one is it? C for carboxylic acid, right? C is for cookie, right? You see this thing, you're like, come on, how could I mistake that? That thing is gigantic, right? It goes from 2,200, it goes from here to Pikes Peak. Like that thing never ends. That's the biggest stretch I've ever seen, right? So carboxylic acid. And if I asked you guys, well, what's that? That's the most intense stretch in the whole spectrum. What does that come from? Anybody remember? What part of our carboxylic acid does it come from? What's the C double bond O? What's the technical term for it? It's the carbonyl. Yep, it's the carbonyl. Yeah, great. Carbonyl, carbonyl, either way is fine with me. Okay, good. There you go, rocking and roll. And I would say B and D. There's nothing there. So I'd say they're not alcohols, are they? And they're not carboxylic acids, are they? You're like, what kind of boring garbage? No, these are still good IRs. They're just not alcohols or carboxylic acids. Now again, if I have a primary amine, you see you have the two stretches, right? Symmetrical and asymmetrical, right? Then when you have a secondary amine, you only have one stretch. But if you have a tertiary amine, like the triethylamine here, there's no nitrogen-hydrogen bond in there, right? So just because you don't have it doesn't mean you don't have an amine. It might be a tertiary amine. So this is called a tertiary amine. All right, know what I mean? I've been waiting all morning to say that. I'm kidding. Anyhow, so if you're like, Mr. Dion, you know what? I remember one time I was teaching this lecture, or it was either a couple years ago or something, and I said to the students, I said, does it feel like I'm fire hosing concepts at you? Like, and the students said, yes. And I'm assuming some of you might feel that way too. Do you know why it feels that way? It's because that's what I'm doing, okay? So and you're like, what? You're like, don't think I'm not aware of it, okay? I am totally aware of it, okay? What did I promise you on the first day of class? I said, would we cover a lot of content quickly? Yeah, so, and I'm not saying this to be intimidating. Don't take me the wrong way. Don't say, Mr. Dion's trying to scare me, or as the student said in my FCQ, a flex. So I'm not even sure what that means. But it's not a flex. It's more the reality, right? I did it. You guys are going to do it. The people did it last semester. Your friends who are going to take this class next year, they're going to do it too, right? You're all more than capable of doing it. But yes, some of the lectures in this class, it's a lot of information coming at you quickly. But that's why, and I'm not slagging anybody who isn't here this morning, okay? Everybody has, various and sundry things going on in our lives. But I appreciate you guys coming to class this morning, right? You could have said, well, he posted some videos, I'll just watch that. And I'm sure some of you watched them already, right? But do you feel like there's a benefit to come to class? And right, you're like, oh, some of it's going to ricochet off my head, but some of it's going to go in, right? Some of it's going to sink in here, and I'll see on the quiz, I'll be like, oh, I remember he said that, yeah, right? So I hope you guys get something out of coming to class. So let's summarize a little bit of what we've covered, which has been a hell of a lot of information, pardon my language. Table 14.2, the handout, and again, don't leave without taking one, okay, summarizes some of the key signals that help us to identify functional groups present in molecules. I'm going to give you an abridged version of the table for your quiz. Okay, so you don't have to have everything memorized, but I recommend it. Okay, so I'm going to put a star by this and say, if you've got a good memory, which I know you all do, better than mine, okay, right, Caden? I recommend you try. And you know what? The more practice problems you work on, eventually you're going to be like, yeah, carbonyl, 1700, yada, yada, right? Oxygen, hydrogen stretch, 3200 to 30, right? It's just going to start to stick after a while. You're going to do it with Dr. Lakakula, and you're going to be like, oh, I remember this from class with Mr. Dion, right? Or vice versa. So what do we do when we see an infrared spectrum? We focus on that diagnostic region, right? That's a good place to start. In between 1600 and 1850, that's where we look for our double bonds, whether it's a carbon-oxygen double bond, a carbon-carbon double bond, a carbon-nitrogen double bond. Then between 2100 and 2300, we look for triple bonds. Look, there's only two types of triple bonds we see in this class. One is a carbon-carbon triple bond. The other one is a carbon-nitrogen triple bond. So there's only two possibilities there. Then above 2700, that's where you get into your, is it an OH stretch from a carboxylic acid? Is it an OH stretch from an alcohol? Is it an NH stretch from a primary amine or a secondary amine? We're going to look at aldehydes in a second. So we'll talk about all that kind of stuff, and you kind of put it all together. And so this table summarizes the stretches that we've gone over this morning, and I'm not going to spend too much time on them right now because we've covered a lot of them already. But if I take a look at this reaction that's occurring here, now this is a reaction, we haven't covered this in our class. You're like, I don't know this reaction. Don't worry about it. It's just an idea. Did you know, have you guys run a TLC yet? Thin layer chromatography, right? Probably with Dr. Lakakula, right? Anyhow, when you do that in the lab, right, we use TLCs a lot of times to monitor a reaction, right? You start it at the beginning, you see what's polar, what's non-polar, then you go outside, scratch your, you come back in an hour later, you check it, you're like, oh, something moved, right? Something is happening in here. Well, you can also monitor reactions with infrared spectroscopy. So let's say a person ran an infrared spectrum on this compound here, and they're like, well, hey, I have sp2 hybridized carbon-hydrogen stretching at 3100, right? That's this guy right here. But am I going to see that signal after this reaction is done? Is there going to be are there any sp2 hybridized carbon-hydrogen bonds in this molecule here? Nope, there's none in there. And so what do you see? You'd see here, signal gone. And then you'd say reaction is done, right? You also have a dipole in this carbon-carbon double bond because it's non-symmetrical. That's this stretch right here. Now where is it? It went away because this molecule is symmetrical, right? So there's no dipole in there. Does this resonate with it? Does that make sense to everybody? Yeah, something like that? There you go. And so if we were to try these reactions, what I want you to do before class on Friday, and we'll take a look at this at the beginning of the class, I want you to use the table, okay, that you have in your brain and say, okay, what signals would I see for an alcohol? What signals would I see for a carboxylic acid? How would I know this reaction is complete? If you look at the next one, you notice, and I don't want to give away the answers. I'll let you guys take a look at this one, and we'll do it in the first thing on Friday, okay? We'll take a look at this. All right, so analyzing an IR spectrum. There's a stepwise way of doing it. I'll just be honest with you. I don't follow this a whole lot. I'm kind of like a child in a toy store. I'm more like just give me. I'm like, I see something and I go for it, right? I go for what I see is the most abundantly clear. But if you're a person that's like, I like a systematic approach to everything I do, there's no problem with that. So you start looking around 3400, right? You can tell when you're running by the spectrum, you could look at it and go, not an alcohol, not a carboxyl, right? You could identify that very quickly. Then you'd say, okay, there's no alcohol, there's no carboxylic acid. Is there something just above 3000? Could there be an sp2 hybridized carbon-hydrogen stretch at 3100? Could there be an sp hybridized carbon-hydrogen stretch at 3300? Then you're like, well, there's nothing there. What's just below 3000? Do I have any sp3 hybridized carbon-hydrogen stretching? Is there a signal around 2200, right? Is there a triple bond? Carbon-carbon triple bond, carbon-nitrogen triple bond. then you could look for a carbonyl at 1700, right? You start looking for double bonds. But again, Mr. Dion, I'm just a regular guy. I just look for the good stuff. I'm like, give me the good stuff. And then if I'm stuck, then I start what I call digging around in the weeds and trying to figure it out. But I just like looking for the low-hanging fruit. So that's kind of what they're doing there. All right. So we've got a bunch of compounds. This is a good place to end in the last 5 minutes, is we'll solve this as a group, okay? Just based off of the little bit of information that we have. Again, there's a handout there if you need one. But we have how many different compounds here? We have an alkane. We have an alkane. Here we have an alkene, right? There's some sp2, hybridized carbon hydrogen, in there. Then we have an alcohol. Then we have a dicarboxylic acid. This is malonic acid, if you guys remember malonate, okay, from your Krebs cycle or whatever, so that's malonic acid. Then we have a primary amine. And then what functional group is this one here? Everybody's favorite. It's a very biblical sort of functional group. It's what? Ester, exactly. There we go. So this is an ester. All right. If I call these, I can tell you're champing at the bit already. I can hear it, okay? Everybody is just waiting to scream out. Is there any functional group that you recognize in anything here? Indeed. Who said that? Kevin, what functional group do you recognize? There's an alcohol in there, right? Are you with me on that? Are you with me and Kevin on this? Yes? You see you have a big, beautiful OH stretch here from 3,200 to 3,600 reciprocal centimeters. Now, the fingerprint region, we don't deal with that a lot, but in an alcohol, you also have to have a carbon-oxygen bond, and that would probably be around here. It's usually around 1,000. So anyhow, so we'll just check-a-roo. We got that one. There we go. All right. Is there anything else anybody recognizes in, is there anything you see in A? I'm going to zoom in on A here. Wow. Maybe I'll zoom out a little bit. What if I take my ruler and I draw a line? This is at 3,000. Okay, 3,000 reciprocal centimeters. Do you guys see anything just above the 3,000 sticking out there? No? Does anybody see something there? Does anybody notice this thing? Right? What is that at? Look at this. This is 31, 32, 33, 34, 35. This is at 3,100 reciprocal centimeters. What gives you a signal there? What kind of bond? Could anybody describe it to me? sp2, hybridized carbon hydrogen stretch, right? Look at all those molecules. What's the only one that has that in it? You can just tell me the functional group. Is it the first one? It's not the first one. That's an alkane. It's the second one, right? It's the alkene, isn't it? Right? That's why I zoomed in like this. That stretch, this stretch comes from these bonds, right? That's these things here, right? sp2 hybridized carbon hydrogen stretching like that. You know what? Let's go to the next page. We're going to identify the rest, don't worry. But I'll just throw some low-hanging fruit at you. You guys see anything of note here? I see everybody's grinning, right? Everybody's like practically giggling, right? So if I call this one, I'll call this one E, and we'll call this one F. What does everybody see in E? A giant carboxylic acid about the size of Montreal in there, right? It's a huge oxygen-hydrogen stretch. You also have the carbonyl, right, from a carboxylic acid, so yes. Everybody smiled, like, I'm going to get that one. You will. You will totally nail them. This one is tougher, but that is actually two little baby broad stretches. Do you remember what kind of compound does that? An amine. Do you remember which one it was? Or what do we call it when it's got symmetrical and asymmetrical? It's a primary amine. Yeah, there's only one amine in there. So it's this guy, which is a primary amine. Yep, so we've covered most of them. The only thing left we have is the ester and the alkane. Well, between B and C, right, which one would be the ester? Would it be B or C? Does anybody have a guess? Where does the carbonyl come out? This carbonyl. Where does a carbonyl come out? Around what? 1,700, right? So this must be it, right, Heidi? You have a big old stretch there. So just by process of elimination, I would say this would be the ester, and I would say this boring. I shouldn't call a spectrum boring. That's offensive. But anyhow, I would say that would be the alkane. So that pretty much covers all of infrared spectroscopy. And so what we'll do at the start of class on Friday, there was this question here. I'd like you guys to try that. Try all the practice problems on the infrared spectroscopy, and if there's something you can't figure out, come and ask me. Also, I have your quizzes graded, but I can't stick around. I got to get to class right now, but I'll be in my office, and if you don't see me in my office at 10:50 or whatever, I'll hand them out on Friday. All right? Grab one of the handouts on your way out. They're right here on this banister.